What if I told you that a tiny little snippet of code, something you could just type into a URL, could give an attacker the keys to your entire server? Well, today we're unpacking a really sneaky vulnerability called server-side template injection, or SSTI for short. And believe it or not, it all starts with a very simple question. So take a look at this. It seems totally harmless, right? I mean, it's just a simple math problem inside some curly braces. But what if this little string of text was actually a weapon? One that's capable of compromising your entire web application? The answer might surprise you, but it's a huge, resounding yes. So how in the world does this even work? Okay, imagine you've got a template on your site, maybe for a welcome page that says hello to a user. SSTI happens when the application just blindly grabs a name from the URL and sticks it in that template without checking it first. If an attacker puts special template syntax in their name, they can trick the server into treating that input not as just simple text, but as a command that it has to execute. And just to be clear, we are not talking about some minor bug here. The Common Vulnerability Scoring System, which is kind of the industry standard, gives SSTI a score of 8.6. That puts it squarely in the high severity category. This is the kind of vulnerability that makes security teams drop everything and pay attention, and for a really good reason. So what makes it so dangerous? Why is this more than just a simple bug? Well, because it's not just about making some weird text show up on a page. No, this is like having a direct phone line right into the server's brain. A successful SSTI exploit leads to something that security pros call remote code execution, or RCE, and that is bad. We're not talking about just defacing a website. We're talking about an attacker running their own commands on your server. They can steal all your customer data, read confidential files. I mean, they can effectively become the administrator of the entire machine. It's a total takeover. Okay, so if it's that dangerous, why don't we just find it and fix it everywhere? Well, that's where things get really complicated. The core challenge is the absolute diversity of the technologies that are involved. You see, modern web apps use things called template engines to build pages on the fly. And the problem is, there are dozens of them. You've got Ginger 2 for Python apps, FreeMarker for Java, ERB for Ruby, and the list just goes on and on. Each and every one has its own unique syntax for executing code, which basically creates a minefield for any security scanner that's trying to find these vulnerabilities. And this is exactly where most of those automated scanners just fall flat. They can't handle all this diversity, and it leads to a ton of false alarms, or worse, they miss the vulnerability entirely. To solve this, you really need a smarter, more specialized tool. For example, a tool like CERT-X-GEN is built specifically to test for tons of different engines at the same time, and, this is the crucial part, to intelligently verify the results it gets back. So how does a smarter tool actually go about tackling this? Let's break down this strategy, because it's pretty clever, and it's designed specifically for this messy multi-engine world we're talking about. Okay, this is one of my favorite parts, because it shows the really clever logic behind the test. Why use multiplication, 7 times 7, instead of, say, addition? Well, think about it. The number 14 from 7 plus 7 could pop up anywhere on a page, in a price, a date, whatever, which could cause a false alarm. But the number 49? That's way less common. Seeing a 49 in the response is a really, really strong signal that the server actually executed our code. It's a brilliant little trick. And this is where the real intelligence kicks in. A smart scanner doesn't just send one payload. It fires off a whole series of them, and each one is custom crafted for specific engine syntax. It's like trying a bunch of different keys in a lock. When the server responds to one of them by printing out that magic number, 49, the tool knows exactly which engine is running. It's basically fingerprinting the technology to confirm the vulnerability. So let's put it all together. This whole detection process isn't just random guesswork. It can be broken down into a really methodical 4-phase investigation. Okay, so first up is reconnaissance. This is where the tool injects all those different mathematical payloads into every part of the request. Next is analysis. It carefully scans the server's response, and it's looking for one thing, that magic number 49. Then it moves to verification to make sure the flaw is real and not just some fluke. And finally, once it's confirmed, it enters the reporting phase, where it documents exactly which engine is vulnerable and flags it as high severity. All right, so we know how to find it. That's great. But what's even more important is, how do we defend against it? Let's switch gears and talk about the practical stuff, prevention and remediation. Your first line of defense is always going to be secure configuration. Most modern template engines have this absolutely critical feature called auto-escaping. You have to make sure it's turned on. It basically tells the engine, hey, treat any special characters as just plain text, not as code. And there's a golden rule here. Never, ever, ever let user input define the structure of the template itself. That's just asking for trouble.
The second pillar of defense, and this one is huge, is rigorous input validation. You have to operate under the assumption that all user input is hostile. That means sanitizing everything. And don't try to play whack-a-mole by blocking bad characters. That's a losing game. Instead, you want to use an allow list to define only the characters you know are safe and just reject everything else. This is especially important for things like curly braces and dollar signs. You have to tell the template engine to treat them as literal text, not powerful commands.
Now, for all you developers watching, this often comes down to simply knowing which functions in your framework are safe to use. In the Python framework Flask, for example, you should always be using render template because it loads a predefined secure file. The dangerous alternative is render template string. That one builds the template on the fly and can easily inject user-controlled data right into it, creating a textbook SSTI vulnerability.
So, if there is one single thing to take away from all of this, it's this. You can't treat SSTI detection as a one-size-fits-all problem. It just doesn't work. Finding this vulnerability requires a surgical approach. It's all about using those engine-specific payloads and then intelligently analyzing the response to spot that hidden execution.
And that kind of leaves us with a final thought, doesn't it? SSTI really became a major threat as our web frameworks got more and more complex. So as our technology continues to race forward, it really makes you wonder, what's the next critical vulnerability that's already out there, just waiting to be discovered, hiding in plain sight?